Welcome back. Today we will cover the rest of the IRT lecture where we left off last time. If we have time, we'll go ahead to the next lecture, which is Dichotomous IRT models. But before I did that, I was reminded by somebody the other day that we hadn't discussed the formative assessment 5 and sort of covered some of the questions for it, and they kind of asked that we maybe review it. No, that's a great idea. So this was the formative assessment that was in the middle of October, beginning of October, where I was on my last leg of a bunch of travel. And so I thought I would just cover it now. Does that sound good? Why not? What's an improper prior distribution? I'll start there. I'll just say it, an improper prior, a prior that is not a proper distribution itself, right? So a distribution has to sum or integrate to 1, like a probability space. An improper prior may not do that. A drawback to using these prior distributions is that you could have convergence issues. You can have all sorts of other non-standard sort of results. The bigger thing is, should we get into a little Bayesian trivia here? I've mentioned this before, but I'll mention it here too. When you don't specify a prior distribution in Stan, we all know it defaults to a uniform prior across the real number line, right? And a uniform prior is great. The density function is super easy, right? Uniform prior looks like a big rectangle, so it's the area of the rectangle, right? Length times width, whatever you want to call it that, right? That area underneath it. Well, sometimes if we say the uniform ranges from A to B, then our PDF for it will be 1 over B minus A for every part of the uniform distribution, so every value. In Stan's user guide, it says when you specify no prior, it defaults to a uniform distribution, unit norm, over the real number line, which would be negative infinity to positive infinity. Nifty. Evidently, autocorrect takes infinity to nifty. Anyway, so as you might imagine, this presents a bit of problems because 1 divided by infinity, nifty, 1 divided by minus a negative infinity, what does that become? Undefined again, right? You can't have a infinity plus infinity, it's still infinity. 1 over infinity, well, 1 over infinity goes to 0 as the limit goes to infinity, but we don't have that. So we call that improper. However, are you ready for the computer science nerd in me? Have you ever talked about what a floating point number is? Does anybody know what a floating point number is? A floating point number, we can define it as, it's a number in the computer that has decimal values, right? Do you know how it's formed? Floating point numbers are formed through a series of discrete values. So what you end up getting is a translation of a bunch of binary digits to the number that happens to be the positive part and the number that happens to be the exponent. So what I'm arguing there is it turns out that when Stan does this negative infinity to positive infinity, in the computer there's no such thing as infinity. In fact, it's a discrete distribution. There's only so many different permutations. There happen to be billions of permutations of zeros and ones that lead to floating point numbers, but they're all equally likely, which makes this a proper prior once it's in the computer. But if you specify it theoretically, mathematically, it's an improper prior. Are you following me? Questions on that? Once again, the difference is in the computer, it's a proper prior because all numbers in the computer come from discrete permutations of binary digits. And every one of those permutations is equally likely. It's basically a discrete uniform distribution. Anyway, Step 2, in some models, in example 3a, we've used exponential distribution as a prior distribution for the residual standard deviation. The residuals of our linear model. Why do we do this? What happens when we increase or decrease the value of the hyperparameter? Well, we use an exponential prior because the range of exponential goes from 0 or is positive, and standard deviation should be positive. And we saw what happens when we change the hyperparameter. As the hyperparameter gets smaller, the distribution is flatter. As the hyperparameter gets larger, it starts to push its prior distribution's mass, its density, towards 0, right? And I think we played around with that in class. All right, number 3. In some models of example 3, A, we have not explicitly defined prior distribution for the model parameters. What does Stan do in these situations? Defaults to uniform. Is it advisable? I try not to get too much into the weeds on priors. Let's put it this way. In a Bayesian sense, if you're talking to the average Bayesian, they would say, that's a terrible idea, because Bayesian is about belief. But, you should be capturing your belief about parameters with your prior distributions. But what if you don't have beliefs about parameters? What if you know nothing? A uniform distribution seems suitable then. Beyond that, there are some cases in estimation of the residual standard deviation where a number of papers in the early 2000s showed sort of the impact. Uniform may not be the best choice of prior for bias of posterior estimates and so forth. So you may see that to be an issue. But I would say it's not terrible to do it, but if you talk to a dyed-in-the-wool, strong Bayesian, they will say it is. Does that make sense? How many of you like uniform priors? How many of you don't like them? All right, never mind. Let's see here. Question 4. In some models, in example 3a, we've used the normal distribution as the prior distribution for some parameters. What happens when you use it 0 and 1 as hyperparameters for mean and variance in our model? Is it advisable? Clearly, a mean of 0 means you believe the parameter should be 0. A variance or standard deviation of 1 is somewhat highly informative. It sort of takes the mass of the normal distribution and centers it between -3 and 3. So, to me, there are cases where normal hyperparameters, standard normal prior, or hyperparameters of 0 and 1 for mean and standard deviation are fine. I think there are places where parameters might certainly fall in that range. And then there are other cases where it's not so fine, right? So if you're in a linear regression and your regression coefficients are all sorts of numbers, somewhere between, some are 10, some are 200, this probably won't work. If you're in a psychometric model and you're putting this on the A parameter or the discrimination parameter, hey, that may not be so bad. So it depends on the situation. How's that? All right. We have reviewed how to use matrices in Stan code. Why have we reviewed how to use that instead of enlisting each element? The answer is Stan gets more efficient. It's easier to build one set of code for everything. And then, what is the function of generated quantities? It's to make your life miserable, right? No. To make your life better. That's what it is. How is your life better because of it? Because there are a lot of things we end up doing with posterior distributions that we have to calculate after the Markov chains run. Generated quantities keeps track of that for us. So if we sort of do some pre-planning, it will be built into compiled code, and it may even run faster than if we built it after the fact in R. Okay? Questions on formative assessment 5? I'll take that as a no. All right. Any questions about what we covered last time in class? Also take that as a no. No questions. Perfect. I believe we left off talking about the discrimination difficulty parameterization. And I sort of went through that pretty quickly. But let's just talk about that a little bit more. This is about right where we left off the last time. I think we did. Maybe a little bit further. We talked about this, I know. I said you could build it into generated quantities as well. But if you estimate it, the part I was dwelling on was the fact that the numbers aren't entirely equal, right? Right. So here, difficulty parameters, the posterior distributions are a bit different. And do you want to talk about why? Nah, I don't know. Think of it this way. Here's our formula. Right? This is discrimination difficulty. This is slope-intercept, right? So guess what happens in slope-intercept? We defined in our estimation just a few slides ahead that mu should have a normal distribution as a prior, and lambda should have a normal distribution as a prior, right? We all think that's a pretty good idea, mostly. No problem. Well, similarly, a couple of slides ahead, I define in discrimination difficulty form a normal prior for the A parameter and a normal prior for the B parameter. So guess what's going to happen to our posterior distribution comparatively, right? Think about it here. The comparison I want you to make is if I put normal on A and normal on B, and I wanted to compare it to something that looked like the slope-intercept form, then look what happens. My intercept parameter is actually a product of A times B times -1. So think about those prior distributions. If I'm going to form a generated quantity where I'm calculating A times B times -1, the impact of the priors are multiplicative in that case, right? So instead of saying that this has a normal distribution on A and B, or excuse me, a normal distribution on the intercept, what I'm saying is it actually has a normal distribution on A and a normal distribution on B, and if we were to multiply the two together, you would envision that prior would almost have like a multiplicative part to it. It's a little bit more complicated than that, but you can see it conceptually. What do you think? You see why that would be different? And that's what ends up happening. It's a little distasteful for me because I'm used to frequentist world without the prior, where we can convert from one to the other and have everything be the same for the most part, as if we estimated it itself. But here you can see there's some potentially sizable differences in parameters, right? Like, so the mean for discrimination difficulty of the B parameter was 1.48. But if I estimated the slope-intercept model and then used generated quantities to estimate my B parameter, it's 1.34, right? Not only that, the posterior standard deviation is much smaller in my slope-intercept model than it is in my discrimination difficulty model. And our range for where our credible interval happens to be is also smaller. So you can see there's some sizable differences potentially. Those differences will go away as you have more data. We only have 177 observations in this case. So as you might know, if you took IRT class in educational measurement, we always say 177 cases. It's hard to do IRT on. Yeah, it happens. But does this bother you? Is anybody bothered by this comparison here? Not too bothered. Nobody looks especially sad. I mean, I only see a few of your faces, but those I'm seeing are happy. Look happy to me. Thanks for showing your camera. Well, we can go a step further. As I mentioned toward the end of Tuesday, the discrimination difficulty model, this is the EAP estimates of our parameters. And here's our slope-intercept model estimates. They're highly correlated, but the scale is different, right? The range is wider in discrimination difficulty than is in slope-intercept. Same thing with discrimination parameters. You can see the same here. But theta tends to be highly related as well, too. So we're estimating the same idea, it's just the scale is changing, right? The parameters are mostly the same. Okay. Any questions about any of that? I spent more time on that because I know I was running out of time last time. I went through it quickly. All right. Shall we move forward? Next, IRT is full of extra stuff. So let's calculate some extra stuff in IRT. What am I talking about? Well, a lot of times we want to see, we want to take our IRT model results and construct things like test characteristic curves, which is the comparison of the latent trait value with the sum score itself, the expected score. We may want an item information curve, right? The idea of information for an item is how much information about the latent trait the item has or contains in it. And that varies by the location of the latent trait. So we'll have an information function, information on the y-axis and theta on the x-axis. We may also have a test information function, which is the accumulation across all the items as well. So I'm going to show this for the discrimination and difficulty parameterization. But as you know, if we're just changing parameters around, we can calculate these with any type of parameterization, slope, intercept, or discrimination difficulty. And the key is this. What I'm going to do is I'm going to import a few values of theta into Stan, and then for each value of theta, calculate the TCC, IIF, and TIF, test characteristic curve, item information curve, and function, and test information function for every value of theta in Stan using that generated quantities block. Because I insist that generated quantities makes our life better. That sound good? Would you agree that generated quantities makes our life better? Yeah, maybe not. Probably not something you'd answer on my formative assessment. But even if you did, you get full credit, because that's how it works. Thanks, Sergio. Got a check mark. I like it. All right, so first we're going to create a range of theta values. With a standardized theta, we would expect values between -3 and 3. So I'm just literally going to cover the range from -3 to 3, inclusive of the endpoints. And I'm adding 0.01 values to each successively, right? So basically, I'm going to import into Stan the sequence of numbers from -3 to 3 with every hundredth of a decimal place. So here's the first 10 values of that. There's a lot, right? That's a lot of thetas. The test characteristic curve, turns out it's formed by the sum of the expected value of the probability of each item, conditional on that value of theta. So let's talk about that real quick. Imagine we take the very first value of theta, -3, we plug it into our inverse logit function. Out comes a probability. That probability represents the expected probability that person with a theta of -3 answers this item correctly. The test characteristic curve is the sum across all items of their respective probabilities. So what it comes up with, what you can say is the y-axis on the test characteristic curve turns out to be the expected number of points scored, raw score points scored on the test itself. Okay. So, in Stan, here you have it. Here's our test characteristic curve. If you wanted to see how I built this into Stan, you can actually go into this section here. I import theta vals right there. I go down to generated quantities. And then for my test characteristic curve, I have to condition this on val means that value of theta. And right here, there's quite a few values of theta between -3 and 3. And this basically becomes a sum where we have the test information function sums for every value plus the inverse logit of your item response function. So here in this inverse logit function, it's putting what's in the parentheses into this e over 1 plus e for us, which is nice. And then the a parameter is being estimated in the chain. The theta vals value is that fixed value of theta, starting at -3 and moving in 1/100th of a unit increments. And then b is in our chain as well too. Whoops. So, any questions on my code? Excuse me for just a moment. I need to blow the nose, so I'm going to mute, and I'll be right there. All right, sorry about that. I feel like I'm like at the dinner table or something. It's not good manners to blow your nose at the table. Probably not good manners to do that in front of class when we have an online class. Am I right? I don't know. Maybe it's more acceptable in person, but we're not in person right now. Okay. So this right here shows us the test characteristic curve. Let's talk about it a little bit more. And this is, again, is this Bayesian idea of error and how we can easily display or think about error. the dashed red line is our EAP estimate of the test characteristic curve. Right? The black lines represent one posterior draw's test characteristic curve. So the y-axis represents the number of correct item responses, right? This is the expected score in raw data units, and the x-axis represents the theta ranging from -3 to 3, this hypothetical theta that I mentioned before. And what you can see with this is consistent with what we saw with some of our other plots, I think that we got into before. For instance, when we calculated the item characteristic curve, we saw a bunch of error around it too. But here what we can show is, remember, this is a scale where each person, the theta represents a person's tendency to agree with conspiracy theories or believe in conspiracy theories. So a person would have to have at least an average theta to have a just slightly bigger than 0 chance of even answering yes to one of those items. But really, if you want to talk about once theta gets higher and higher and higher, we really do have those people get the chance of endorsing items goes up markedly, right? Between 1 and 2 standard deviations after the above the mean for theta. Similarly, on this, if we wanted to do sometimes in a testing program, you may want to have a score that you give people that's on the raw score metric. So sometimes we take our latent variable and we convert it to a raw score variable using the test characteristic curve. And with this process right here, you can go and actually create a standard error of your test score, right? So for instance, for a person who's a theta of 1, you would say their raw score for the test, for the items itself, the sum of the item responses being 1, should be somewhere between, a little about 1/2 all the way up to almost 2.5. Right? So not only can you give a test score for each person, you can also give a standard error around that test score as well, which is nice, I think. Any questions or thoughts on this? Nah. All right. How about item information? All right. Item information. This is the not IRT class version of describing this. In IRT class, we spent a long time on this concept because item information is important in building different building assessments using computerized adaptive assessments and understanding which items are most informative about the latent trait theta. Item information here, for us, the way that we define it is the derivative of, the derivative of the item response function with respect to theta, right? And actually it's the second partial derivative with respect to theta. Now, interestingly, if you think about how we form item information, we go back to our model data likelihood. Remember the model data likelihood for theta? I actually have it in our slides here. Let me see if I can find it real quick. This is our model data likelihood for theta right here, right? If we differentiate this, if we take the log of it, differentiate twice with respect to theta, that's where each item's component, once we take the log, is the contribution of information for one item. And what we end up getting in this sense is also how we derive the test information function, right? However, what's missing from this equation in a Bayesian sense? We don't have a prior distribution on our items anymore. So that may or may not be the sense. But basically the idea is, let me get back to it. The item information function itself is what we derive for MAP estimates itself. So this is telling us information that is from the maximum of theta itself, not the posterior mean. This is not, so what I'm saying with this is this information function describes the sort of the curvature of our posterior distribution at its mode, not at its posterior mean. So it's a little bit different than posterior standard deviation. But we can still calculate it, and we can still use this. And how we calculate it and use it, this is our information function. You can find this, if you're in IRT textbook, sometimes they call the expected probability of a correct response P. So this is P. and then 1 minus that. Sometimes they call that Q. So the formula, the classical formula you may often remember is A squared times P times Q. That's just how it tends to work. We can calculate this in stan again. So here I have my item information function, but now I have to have one for each item and each theta. That's why it's a matrix. And here in my loop across all of the items, which is also within the loop across all of the thetas, I calculate this item information. Actually, it's not. Yes, there it is. There's a loop for all thetas right there. So there's my calculation of the information function. And then this is what it looks like. This is item 1. So item 1, the way we typically read this, again, the red dashed line is the information function if we just plug in the EAP value of A and the EAP value of B. And we would say, based on the EAP value, the area of maximum information is probably somewhere about 1 1/4, right here. But take a look at the variation, right? You can see that wiggles around quite a bit. So even though we think it's right here, it's not entirely certain that it's right there. This wiggle that you see here is kind of important if you think about it. Because, again, information, item information, we use this to build test assessment forms with a certain test information function, like where we concentrate where information is. And based on the spaghetti plots of each posterior draw, we would say that maximum information for this item is somewhere between 1/4 and maybe 1 and 1.75. But really the peak of it's right about 1.25. So you can envision a case where if we ignored all the variation in item information and we go and try to build a test with this item, we might not get an exact good looking test form. Now, all these things I'm telling you, we know about. IRT theory, we've known about this for many years. That's why we often say IRT should be is like a large sample method, because as n goes up, your sample size goes up per item, this variation gets shrunken, right? The model data likelihood starts to win, and if you have thousands or even tens of thousands of observations, you're not going to have as much variation. So in small samples, though, this is a big issue in IRT. So I personally love Bayesian in small samples for part of that reason. So, questions on any of this? I see no questions. All right, let's go to the test information function then. The test information function is listed right here. The test information function, because we're Bayesian, we also have to think about it as including the prior distribution of theta. Whoa, hold on a second here. What am I talking about? So this is what I realized halfway through describing before. Test information comes from the sum of item information, but it also it really is based off of differentiating the log likelihood, model data log likelihood, twice with respect to theta. Right? It tells us how much information the test has overall about the trait across the range of trait values. But in the Bayesian sense, our model data likelihood isn't the only component talking about theta. There's also the prior distribution of theta. And so if we have to go and differentiate that too. So test information that you're seeing from me, this is your traditional test information function, the sum of item information. But because we have the normal distribution on theta as its prior, we have to differentiate that as well, which leaves a -1. So what you see here is the Bayesian version of a test information function, which considers not only the model data likelihood of theta, but also the prior distribution of theta as well. And for us right now, that just turns out to be a constant. If you have different priors, so for instance, if you're Bayesian updating, the idea that maybe each person's theta you're going to update periodically as you go forward, there may be different versions of priors as well too for each person, and that may be a little bit different. But let's take a look at this test information function, shall we? It's really hard to see the scale of this. Test information is much larger than item information because it's the sum of all the item informations. And here, what you end up seeing is these numbers go from somewhere between 0 and, I don't know, 5,000, right? Test information in a non-Bayesian sense, if we take 1 over -1 times the square root of that number, 1 over the square root of that number, we end up getting conditional standard error of theta. Although in our sense, this is not true because we're in the Bayes world. This is another shape of the test information function. Once I smooth that distribution, you'll see that with the posterior draws, we get some really wide values of really high values. But once we smooth everything out, it really starts to look like this. And we can tell that our areas of maximum information for the test is somewhere between 1 and 2. Does that sound good to you? All right. Question for you. Psychometric question for you. Going back to item information here. What do you think the item information plot in the CFA model looks like? Because I didn't discuss it in CFA. Turns out it's flat. Right? There's no difference in information about the item across the range of theta. Have you ever seen that before? So, if someone says, I'm going to do a computerized adaptive assessment with CFA, how does that item pool work? If the information function is flat. Here, let me make a better story. So, in a computerized adaptive assessment, oftentimes we seek to give a person the item that's maximally informative for them. There's some other constraints. There's plenty of methods out there, different stratification methods and so forth. But for us, let's think of the maximum, right? So if we have a person who comes along and their theta value happens to be 1.1 or 1.2, this item would be a good item to give that person because it gives a lot of good information to it, right? And as soon as they answer that question, let's say they say yes to it, they might move up in their theta. We find an item that has good information for them at that range and give them that item. If we were to think of a computerized adaptive assessment, and this line is flat though, and we want to give a person the maximum information item, we would always give the same sequence of items. Because the most informative item is always the most informative item, regardless of where theta happens to be. Right? So, in a computerized adaptive assessment using a CFA model, you will always give the same pattern of items. And if you always give the same pattern of items, there's another term we call that a fixed form assessment. Right? It's always the same set of items, always the same set of people. So, if you get into comps and you want one of my comps questions, I might ask you something like, tell me about, build a computerized adaptive assessment with a CFA model. Can you? No, not with the model the way it's parameterized the way it is. It just results in fixed forms. So, but, are you ready for the other kicker with this? If you're like me, you're thinking, IRT sounds so good. How do I sign up for IRT? I need more IRT in my life. Anybody thinking that? Look, I can build out adaptive assessments and blah, blah, blah. Cool, right? Guess where that flat line would be in CFA compared to IRT if we were to superimpose the two somehow. Although they're on different metrics, but let's just think about it. Because CFA uses a normal distribution, remember, it treats each observed variable as continuous. So, it's not like a Likert scale where we give it 1, 2, 3, 4, 5. In a CFA model, if you had a value of 1.05, it would mean something different than the value of 1, right? So what I mean with that is there's information by fractional bits of information just by considering the decimal values in between discrete answer choices. That's what a continuous distribution does. Well, it turns out, by comparison, the CFA, if we could come up with a way to draw it, it would be much higher than IRT. Right? It would be higher because that allowing for a normal distribution on a continuous variable, it's built to have sort of finite measures of difference in likelihood based on small differences in the trait itself. So that is highly informative. a discrete distribution like Bernoulli is either 1 or 0, right? Very one probability regardless. Everybody who's a 1 gets one probability. So in many ways, CFA would be like, it's highly informative, but it's probably misleading because it's not applied to data correctly. So what am I saying with all this? When I took IRT class and I saw all this extra stuff that IRT could do over CFA, I was like, wow, that's awesome. But then I realized, actually, if you want to compare it to it, this is sort of, have you ever heard the saying, making lemons from lemonade? Like, making lemonades from lemon. If life gives you lemon, make lemonades. Like basically turning a negative into a positive. The negative about IRT is with binary data, you do not have any, you could not get less information about a person than a binary piece of observation data. That's it. There's no less information you can get. It's a bit. It's 0 and 1, right? That's it. So this information turns to be much lower. And then CFA, once we ignore discrete, that information must be higher. So it's almost like, yeah, that's CFA is overly optimistic, but it turns out to be a much higher and flatter information function. So I thought I'd stop there and talk about that a little bit. What do you think about that? Ever considered differences in psychometric models like that? All right. Vladimir. Yeah. Mm-hmm. Yes. Second question first. Does the flat line related equal errors across CFA? Yes. Really, it's equal. The idea is actually more equal to me, my conjecture is it's in a normal distribution, there's two components. There's a mean and the variance. And because they're separate, the variance and the mean are independent. And so that's why you get this flat line. Whereas in IRT or with Bernoulli data, once you know the mean, you know the variance. And not only that, the amount of variance you have is limited because as the mean moves forward to 1 or down to 0, the variance gets smaller and smaller. And so because they're sort of yoked together, I think you end up getting this nonlinear information function, at least to me. That's my conjecture for it. The first question about what is the scale of information, that's a great question. If we look at test information, the way I used to describe this is the following. We often look at test information, and again, a non-Bayesian version of test information, like 1 over the square root of that is our conditional standard error of measurement for theta, right? And so conditional standard error of measurement for theta, that's more on the theta metric that you're used to seeing, right? So if we were to talk about what a good information is, we could sort of backtrack it and say, what's 1 over the square root of it? That's its in that sense. So if test information is the sum of a bunch of item information, right? And item information turns out to have a scale that's much smaller than test information. A highly informative item to me would be one such that it really changed the posterior standard deviation high. But I can't really ascribe units very easily with posterior standard deviation. You'll see Lisa Hoffman, and actually this is based on our conversations. She and I used to think about this stuff. We like to say, if you have a test information, you can actually convert this to reliability, which is 1 over 1 plus the standard conditional standard deviation of theta. And when you do that, a test information of 4 brings out a reliability of 0.8. I will say two things about that. Number one, not everybody agrees on that reliability formula. Even if I think we're right, not everybody agrees, and everybody thinks they're right. So realize that. And number two, in a Bayesian sense, it's not as direct as to what test information means. Because test information, again, when you take a derivative or a second derivative of a likelihood function, you're describing its curvature at its mode or its maximum. And for us in Bayesian world, we don't necessarily need the curvature because we have the whole shape of the distribution itself, the posterior standard deviation. So there's a more tenuous relationship between test information and posterior standard deviation in Bayesian as well too. So hope that helps answer your question. There's not a lot of, I can get close to saying a lot of test information is 4 or higher if I want to go with that reliability measure, but not everybody agrees on that. So I hope that answers your question a bit. You're welcome. Yeah, I completely agree. Reliability is easy to understand. For whatever reason, there's 4 or 5 different versions of reliability once you talk about the latent variable itself, if not more. And so, I know why I have my version, and I can describe why that's the case, and then someone else will tell me why I'm wrong, or vice versa. So I just wanted to leave some room to say that I'm not always right about this, or not everybody will agree, but I'm right and they're wrong. So do we all agree with that? I'm just kidding. Don't answer that question. I know you all want your grade and you're all doing well. All right. Let's talk about a few other IRT models, shall we? How to implement them. I showed you the 2-parameter model up to this point. Either is slope-intercept form or as discrimination difficulty. Correct? For us, we can start talking about this a little bit differently. There are, as you know, a ton of IRT models out there. And the 2-parameter logistic model we had may look like this right here, but there's a slight change that we're going to need to make in some places, right? For instance, Bernoulli logit is the issue, right? Bernoulli logit is super convenient, right? Why is it convenient? Because I don't have to go and say, for instance, take the linear predictor, right? In this case, A times the quantity theta minus B, and then translate that to a probability by putting it in the inverse logit. It's already built in, right? So what Stan does is takes the term in the parentheses, puts it in E over 1 plus E to that term, and takes the probability, calculates the density of the value, the likelihood value based on it, right? However, some of our IRT models need you to not do that, need you to form the probability itself. For instance, the 3-parameter model or 4-parameter model, you'll have to work with probabilities. So we're going to have to make a change to the Bernoulli logit, and instead we're just going to use a Bernoulli log likelihood. So what do I mean by that, right? To sort of, again, teach you one thing at a time and then make things more complicated, what we will do is take that last slide's syntax and build an equivalent model with not Bernoulli logit, okay? So it turns out in Stan there's a Bernoulli function. It's the PDF of Bernoulli, right? And when you say y follows a Bernoulli distribution with this tilde term, y again has to be an integer just like in Bernoulli logit. So everything about y is the same. But when you use Bernoulli, what it expects to have as its argument is a probability. Right, so that's that probability in the Bernoulli function, the pi, right? Remember, a Bernoulli PDF is pi to the y over 1 minus pi raised to 1 minus y. Remember that? This is the pi in the function right here. So we can take our linear predictor from IRT, A times theta minus B, and put that into the inverse logit function. Right? Inverse logit is E to that over 1 plus E to that. So that's the conversion to probability. So it's a slight change, right? Instead of having Bernoulli logit and just passing to it the inside part of the exponent in the IRT model, we just say Bernoulli, and we pass to Bernoulli the inverse logit function, and inside that, we pass to that the IRT model's linear predictor, right? But the key, right, in your mind, is that now this term inside, this inverse logit, that's a probability. So anytime that you need to work with a probability or modify a probability because your model has changed a bit, you can do so and just use inverse logit. And I'm going to show you that in the 3-parameter in a few slides here. How are we doing so far? Questions with any of this? No. We doing okay? Riveting, isn't it? This is like watching your favorite drama play out. Like, what's going to happen with inverse logit? I gotta do something to break it up. It's an online class. We're looking at syntax. Can we make some stat jokes? It's Halloween, for heaven's sakes. I can't even throw candy at you. All right. Anyway, here's the one parameter model. I said all that to say I'm going to show you this with a 3 parameter, but I'm going to start with the 1 parameter model. In the 1 parameter model, we often phrase it as theta minus b. Thanks, Sergio. Thanks for the that looks like Halloween right there. Either that, or in my house, since my son has pneumonia, that might be a cough drop. Anyway, ruining Halloween. We're handing out cough drops tonight for Halloween. How disgusting is that? I'll stop the digression. So, 1 parameter model, and actually, Sergio, you might be able to tell me better than this. I'm calling it a 1 parameter model, but to those on the Roche community, sometimes they're Roche models and sometimes they're not. And Sergio trained under someone who was a specialist in Roche, and so that's why I'm picking on him. So I'll just call it 1 parameter and leave it agnostic, because I don't know where Roche applies. Sergio, what do you think? All right, so Roche model is where the A parameter is set to 1. A 1 parameter is where the A parameter is any other value. But I'm going to say this. Here we go. The interesting thing about the Roche model, again, I can phrase the model down here. Sorry, it's at the bottom of my screen. Y follows a Bernoulli distribution. Again, when I do that, I use the inverse logit. Technically, I don't have to do this for Roche. Right? The 1 parameter model is already enclosed. There's nothing multiplying the probability. So it's kind of overkill for me to show you this. The other thing I wanted to show you, though, is, and this, Sergio, maybe where it's not a Roche model, when you set one or more item difficulties, or item discriminations / factor loadings to 1, once you fix their value, in this case they're all equal to 1, you can estimate the standard deviation of the latent trait. So I can go and estimate the standard deviation of theta right here. So now, instead of having a standard normal distribution for theta, I can go and estimate its standard deviation. Turns out that's actually equivalent to a 1 parameter model where all the A's are equal to standard deviation of theta. Go figure. Right? You can actually do the math and show they're equivalent, so I don't know if that becomes Roche or not, but leave that alone. The other part of that is now the standard deviation of theta is an estimated parameter, and so we have to give it a prior, and so I can just put a prior distribution on it. So this is what we would call an empirical prior. It's also the first place that we see where we can go and estimate or set the scale through estimates, not by fixing it, the scale identification of theta. Any questions on any of this? It's kind of cool, right? Maybe. How about the 3 parameter model? Now, this is where Bernoulli logit really matters. In the 3 parameter model, the term in the brackets right here is the 2 parameter model. But then we multiply that by 1 minus a C parameter, and then we add that C parameter to the probability. So what's happening in this sense is, if you think about the right-hand side of this equation, as theta goes to negative infinity, this probability goes to 0. So the shape of the item characteristic curve, and actually as this probability goes to 0, it drags with it the term multiplying it to 0. So all of that goes to 0. And so basically the lower asymptote of item characteristic curve happens to be what the value of the C parameter is. Right? So the C parameter is on the probability metric. But A and B and theta are on the logit metric. So we have to combine both to build this model. So let me just show you the syntax real quick. This is where the Bernoulli function really matters, right? So you have Bernoulli here, and inside of it, you build the probability based on the formula you see above. The C parameter, the lower asymptote, plus 1 minus the C parameter, the times that inverse logit function applied to A times the quantity theta minus B. So that's where C gets entered into the model. But let's talk a little bit more about C. What do you know about the 3PL? Three-parameter model. Let's see here. C sometimes gets called the guessing parameter, the pseudo-guessing parameter. It's called that because you can envision if you had a multiple choice item with 4 answer choices, you would think a person that has no ability whatsoever would randomly pick between the 4, and so that lower bound of probability of correct response would be 1 over the number of choices, right? In practice, C is never that low. In practice, it's pretty hard to write multiple choice items with distractors bigger than that. The other part about C is that when you get to a three-parameter model, it's incredibly unstable sometimes to estimate. It's very difficult to estimate this. And in part, that C parameter is the reason for it. So talking about the prior distribution, the C parameter's range is between 0 and 1. And we haven't discussed anything about variables between 0 and 1 yet in our class, have we? I don't think we have. So when you pick a prior distribution, you often want to pick one with the same range as the variable. Makes sense, right? In this case, we have only a few options. One is a uniform distribution, right? Between 0 and 1, the likelihood value is 1 for all values of C. It's flat. Another version of a parameter that is another distribution that would work for this parameter is something called beta. How are you with the beta distribution? Anybody heard of beta before? Anybody like beta? Beta is an interesting distribution. Let's take a look at the beta distribution from my friend Wikipedia. The beta distribution can take all sorts of shapes. Here is the density function right here with different values. There's 2 parameters in beta, sometimes called the alpha and beta parameters, or the A and B, which is terrible naming. If distribution is called beta, your hyperparameter for it shouldn't also be called beta. Let me just say that right now, right? But that being said, sometimes these are called shape and scale, depending on where you're at as well too. Here, with different values for each of these parameters, you get all sorts of shapes, right? You can get a U-shaped distribution where you favor values at the tails. Sometimes people call this a horseshoe distribution of some sort, right? You favor extreme values. You can get an inverse cone, almost like normal distribution right here. And then you can get a skewed distribution. It turns out if you actually implement a beta with values of 1 and 1, here, let me just plot that thing. I'll bet many of you know what I'm talking about here. Anybody want to guess it before I can plot it? Let's see. Oh, for probability, close to probability. Yes, you can call it a probability. Actually, you can't call it a probability in the continuous distribution, JC. We can call it a likelihood. You can talk about its shape, though. Hang on, it's coming. That's the D beta 1, 1. Look at that. Flat. That is not by chance. That's a uniform distribution. Turns out a beta distribution with values of 1 and 1 is a uniform distribution. So one of the things people really like about the beta distribution is that the beta distribution is really, really malleable, right? If I change some of these values, if I change the second parameter to a 10, now it looks like that, right? If I change the first parameter to 10, make them both 10 and 10, it looks like this, right? How about, can you guess what happens if I change it like that? Oh, wait a minute. It's all sorts of crazy. So the point I'm trying to make with this is beta is super flexible, and we can start with a beta of 1 and 1, right? So this is a way of saying C is, we have a prior distribution that's uniform across C. Now, turns out that's probably not the best choice because convergence issues may be difficult, particularly with small sample sizes. I actually didn't run this on our data. The C parameter is often very, very difficult to estimate. So oftentimes we may pick a beta distribution a little bit differently. In the classic IRT program Bilog, which came out in the 1980s, which was actually, I mean, people still use it today. Any of you use Bilog? Anybody? Anyway, it's still around. You can still use it. They estimate a Bayesian version for the C parameter, puts a prior on it, where the value of the beta distribution is such that the mode of the beta, right, where the peak is 1 over the number of options in a multiple choice item by default. So you would say, I'm most likely that guessing should somewhere be around chance, like if you just randomly selected your response. And I think that's a pretty nice way of doing it. Not bad. Again, we know beta is probably, the C parameter is going to be a little bit higher. All right, a couple more points on C. Because it's bounded between 0 and 1, we need to put the lower and upper bound in. I don't think I've seen the upper before. Actually, I have shown you upper on the integer import of data before. But basically, this constrains C to between 0 and 1. Finally, the 3-parameter model. Why I like the 3-parameter model, to me, is that the C parameter represents not guessing to me. I view it as more of a hedge that your 2-parameter model doesn't fit. It's almost like a fudge parameter, an adjustment parameter. And why I say that is this. If your C is non-zero, the information about theta is reduced for each item. Right? The C parameter actually changes our item information function a bit. The point of maximum information is shifted slightly above where the difficulty parameter happens to be. But the C parameter reduces the information in the item because it's now cutting into the variation in probability that you see here. Right? The range of this term in the bracket is no longer 0 to 1. It's now 0 to whatever this 1 minus the C parameter happens to be. So with C being in the model, what you'll end up seeing is that the conditional standard error of theta will be larger, the fact that comparatively. With it being larger, you say that you have less reliability about the trait, or you have less information about the trait. I like that. And if the C parameter turns out to be 0, it goes back to what it was with the 2-parameter model. So I think that's good too. So I look at the C parameter not because I'm convinced people are guessing, but I'm convinced that our model is not always accurate for our data. And the C parameter will at least hedge our model to make it a little bit more conservative, to not think that we have more information about theta than we actually do. What do you think? Different perspective. Vladimir. You're on mute, I'm afraid. There we go. Mm-hmm. Mm-hmm. Great question. Thanks for the question. The question was, should we consider the 3PL when we're designing tests versus not? To me, when you're designing a test, I don't think you consider any version of the parameters of the model. To me, the bigger thing is the alignment of the items and the construct that you're building, right? The hardest part in building an assessment is the precision of knowing an item actually measures what it purports to measure. So in educational measurement, this is a little bit weirder because most of our tests are such a high level. Like for instance, if we have a K-12 test of math, like a 3rd grade math test or a 4th grade math test, really that math, like you can almost say, oh yeah, there's all sorts of ways that items can be math related. Yeah, that's fine. But really that's such a high level of a reporting information that it's likely that there are multiple dimensions of math that we're sort of ignoring when that happens. right? So to me, when you build an assessment, picking the items, picking dimensions underneath it are paramount. Once you then want to gather data and figure out which model fits the best, then it does become a model comparison task. And whether one parameter or two parameter or three parameter, it doesn't make a difference which one seems to fit best. I would say that the three parameter model, if it tends to fit best almost all the time, at least in the data I've run and worked on. And I think partially that's because, I'm dealing with a lot of educational measurement data at such a wide scale. If I'm fitting a unidimensional version of the model and it's really multidimensional, what I'm picking up with, I believe I'm picking up with the C parameter is a bit of that multidimensionality. It's not fitting well. So my answer is, yeah, consider 3PL, but your consideration should only be once you collect data. And if you're interested in seeing which model seems to fit the best, that works well. The other thing I have to caution, though, is, and some of you in here may end up in educational measurement jobs. In most of those places, you specify the model as part of your contract, right? When you, like, for instance, if you are working at one of the assessment companies that where you're the psychometrician for one of the states that they provide an end-of-level assessment for, an accountability assessment, that contract will specify the model you're running, right? So in many ways, that's it. It is the three parameter. It is the one parameter. And I think in most cases, in the states at least I'm familiar with, those are your choices. You either get the Roche model, the one parameter model, or the three parameter model. For whatever reason, two parameters doesn't show up. So there you go. Does that answer your question? Mm-hmm. Thank you. Yeah, no, and that's it. The results itself. So when you fit a three parameter model, we still interpret the parameters as we normally do. We still interpret theta as we normally do. So I don't know that the three parameter really changes many of our results apart from the values themselves. Like the standard error of theta is usually wider. There's less information about things. But yeah. Thank you. All right. Other questions? How many of you have seen a four parameter model? I don't have it here, but anybody? Want to raise your hand? So it turns out the four parameter model says 3. Who wants 3? Let's go with an even number. Let's get 4. And it implements what's called an upper asymptote. Right? So now the item characteristic curve in the 3 parameter model, which is bounded below by C, gets bounded above by what we sometimes call a D parameter, which ends up showing up here where the 1 is. So as you might imagine, we have to make sure that D is always bigger than C, and in a sampling approach, it may not be that way, so we have to put a constraint in on the D parameter. But you could use most of the syntax right here to estimate the 4 parameter model. Who wants to talk about 5 parameter? I'm just kidding. Actually, I'm not. There are all sorts of IRT models out there. All right, let's talk about normal ogive. Right? I think we said before that we like logits better than probits if we did the probit model. The probit model looks like this, where the quantity A times theta minus B, which is a continuous number, is converted to a probability by looking at the normal cumulative distribution function, right? So like if this were a z-score, what's the probability of a normal curve to the left of where that z-score is? That's what this phi function does. And it turns out in Stan, there is a phi function that you can use. And if you wanted to wrap that around, instead of having Bernoulli logit, or Bernoulli, you would replace Bernoulli with phi. And then you would just import the linear predictor inside phi, the probits inside phi there. Not bad, right? Also, if you remember earlier in class, I talked about other link functions like log, the log link. Well, that would take the place of this inverse logit. But again, Bernoulli would be your distribution. You would just build your link function directly within the parentheses for Bernoulli. So if you wanted to try log, you would take the log part of my slides and implement them here, right? The function, the link function. If you wanted to try complementary log, it would show up here. There are a whole bunch of them. Let me see if I can find a few of them real quick here. There we go. Bernoulli. Oh, it has a link function. Yeah, no, I guess I'm not going to find it here. Never mind. I'll leave it. But yeah, there's a ton. Just take my word for it. Actually, SAS used to have, or still has, a great proc called Proclimix. And it has a ton. It's like mixed models with generalized linear mixed models. Anyway, I'm pulling up his documentation because I'm trying to show other link functions. Just because I opened that door and now I feel not complete without it. So here we go. Specify the link function. By the way, this concept I'm talking about here applies. It's basically what IRT runs off of, right? We switch from normal distributions to Bernoulli. We need a link function for it, and of course it's not found. All right, I'm gonna have to stop. Anyway, what I would have shown you there is like 4 or 5 different versions of link functions, all of which could be used as IRT models if you wanted to. All right, how we doing? JC, yes, question. Yes, actually, good question. Can we leave one out to compare our IRT models? Yes, and actually we're going to do that. This is the tough balance in my head. I probably should have introduced everything at first and then run with it, but I had decided to wait on model fit until we get through all the models and then show the model fit method. So it's coming. It's going to be one of the last set of slides that we get to, but yes, absolutely important. We'll be using it. Almost the same as what you saw it's going to be almost the same as what you saw in the linear model section. It's just the only catch is now we have LOO based on all of the items, whereas in the linear model sense, we only had one outcome. Now we have all the items as outcomes. So it's coming. Good question. And actually, this opens up a window into my crazy brain, which is I debated for years which order to put these slides in. And so I decided it was just hard enough to get us running on Stan. And I sacrificed all the features of model fit until the end. That may be the wrong decision, but hang in there. It'll be coming, okay? Other questions? All right. I love, by the way, so I'm going to stop here today. We won't start a new lecture. We only have 5 minutes left. But I'm just going to say this. I love the Bayesian version of IRT because I think each of these quantities, test information, item information, test characteristic curve, so forth, to visualize the uncertainty in our parameters through that is just a neat way of looking at it. And Bayesian, you can sort of get at that with the frequentist approach if you really thought hard enough. But in Bayes, since we have these posterior distributions and they're easy to work with, they make it very easy to build these plots. So I think a lot about how we often ignore error in a lot of our models, particularly in operation. Like, oh yeah, we have a big enough sample, so A and B are fine. We don't need to worry about their variation. But in the world I live in, that we typically don't have big enough samples. So I find Bayesian to be effective not only for trying to estimate things, but also for making sure I don't claim more about what I'm doing, have more certainty than I really should. Like my posterior windows may be very wide, may be very uncertain, but I don't want to lie about that. So that's part of it. All right, any other questions before we end? Negative. Next week, we will start polytomous IRT models. Homework is due tomorrow. If you have any questions, just let me know. All right, have a great rest of your week. Thanks, everybody. Good to see you.